Thank you.
Hello. Please, the seat. I, yeah, unintended segregation of genders and yeah. All right. Well, thanks everybody for being here today. And for people at home, we're looking and we'll be looking in the future. So I'll see myself in the future, which is hear my terrible accent again. All right. This is a wonderful session. It's an update for projects that are in the CalFlexHub portfolio for commercial buildings going from small to campuses, passing through medium. It doesn't say small commercial. You get it for free. It's also in the other session, but it's better here. The session is also about optimal control, model predictive control, and sort of a new way of controlling buildings that is very innovative and has a lot of potential, especially with dynamic prices. We have wonderful speakers today, Sang-Woo Han, Ettore Zanetti, and Dong-Hoon Kim, who are going to present in a second. So next slide. I'm just going to, oh, that's their name. You already saw kind of the portfolio. It already grew in 10 minutes from Marianne's deck. Now there's 10 more sites. If you keep coming to the presentation, there are going to be more and more sites. The portfolio really covers everything from residential to multifamily, single family, light commercial, campuses, large commercial buildings, and has a lot of sites. So this is an exceptional project that I think are going to deliver a lot of interesting and future kind of spin-off of research in the future. Next slide. The parallel session has the same bullets. These are sort of big innovations that I think emerged from the program. Currently, it's at the end of the third year. What we're talking about here is model predictive control, which has a lot of potential, and we'll see that in a second. On the right is a slide that I had last year talking about how model predictive control kind of plays out, and we can think about it in different subsectors. So in small commercial and residential, it's something that we can optimize and standardize quite a bit because similar systems are pretty similar. On the large campus side, it requires a lot of customization, but you also have a lot of energy to work with. And so that's sort of the approach is feasible, both for small and large. And in the middle, Ettore is going to present about this, is kind of the challenging part of the whole map, which is large buildings, they are custom, each one is different, but they don't have a lot of energy. So that's kind of the whole picture of the research we're doing here in CalFlexHub. Last year, we also had a residential project led by Keaton, who's somewhere here. And next slide. I think we can start.
Hello, everyone. My name is Sang-Woo Han. I'm a technology researcher in LBNL. And as Marco mentioned, I'm talking about the small medium commercial building for the MPC first. Can you go next slide? So we are designing model predictive control for small medium commercial building basically for the heat pump. So we have multiple sites to implement, but our goal is actually making the MPC is available for existing system, which means off-the-shelf heat pump or rooftop units. So that means we are not trying to optimize the efficiency of the heat pump or rooftop unit. We are just coordinating multiple heat pump and rooftop units to shift load and reduce peak demand. And also, one of the big challenges is how to install the MPC to the off-the-shelf product. I'm going to talk about a bit more. But basically, we have this multiple site. So every site has different characteristics and different stakeholders, different occupants. So we're gonna test our technology in their multiple site to further generalization. And we have here the list of the test site. Actually, we added one more interesting part, VRF system, which is a variable refrigerant flow heat pump. And yeah, that one is also included in our portfolio. Can you next slide? So whenever I'm talking about the MPC, people just thinking of it may be too complicated or they need something special product. Yes, well, we need some special products. So here is some configuration diagram. So small medium commercial building has a very standardized structure so far. They have heat pump and they have a programmable or backnet or Wi-Fi in-app thermostat. So basically, they just schedule and the controller is working based on their schedule. But we have a Voltron, which is actually open source control middleware software developed by PNNL, and we installed that Voltron as a middleware in the on-site. Actually, we need to bring a small workstation or small computer there. However, also if we don't, if the thermostat support the Wi-Fi communication, we don't need to have that middle part though. But at least we need a machine somewhere in LBNL or somewhere or cloud server. And the Voltron is getting price signal from CalFlexHub and also some of the time of use signal because we are trying to figure out what diverse opportunity. And also we got the weather forecast and weather data from NOAA. And yeah, there's too much details, but we separate the engines like computing engine, MPC engine, and the middleware control software separately so that making that software can be configured on different sites and different setups like backnet thermostat or Wi-Fi thermostat or Modbus thermostat. And we are also, one of the key feature is we are also testing the CalFlexHub signal, which is on the below. So summer signal is very peak price during the nighttime, actually late afternoon. And spring signal has a little bit different. It's a little bit peak in the morning and peak during the nighttime as well. So can you go next slide? So I'd like to share some of the results. Actually, we have site results for the two sites. One is for, yep. So it's the building is a very photo is very small, but it has it is located in Davis, and it is composed of 13 office zones and one VRF system is working conditioning that whole the whole space. So we actually developed the MPC last year and last year for the coordinating the heat pumps, and we extended like actually modified the objective function a little bit and then extended to the heat pump MPC to the VRF, and thankfully it's working okay. And here is the result of we had so far. It's actually the experiment is keep going. So the top figure is a winter test based on the CalFlexHub signal. So if you see the like blue line, that's a baseline, and the office is starting at 8:30 or 7:30 some near the time, and every VRF is turning on at 8, and you can see the power is peak at during that time. MPC is trying to like preheat the some of the sides, especially the corner side or window side, and then maintain the temperature a little bit higher than on normal baseline, and then it can reduce the peak operation in the morning. And we actually calculate the daily cost, and I found that it's a little saving, but because of the limited number of data we have, we cannot make a clear conclusion. But the cost savings is mainly decided by the on peak and off peak price signal. So if we have a big peak price, then we can expect more savings. And the bottom is our another trial. So we are testing different signals. It's for the time of use signal. So if you see the time of use signal, the dotted line is the price signal, and that's like also although they have like TOU, but it's very kind of flat. So in that part, the MPC is not doing something pretty much, but they have actually demand charge. So by just coordinating multiple the BRF indoor units on and off, like alternate their operation, we can reduce the peak demand, and then the demand savings give us pretty much big cost reduction, like about 30%. Can you go next slide? So this is the same site for the summer trial, and the top figure is also dynamic price. You can see the price is very high during the 4 to 10 p.m. But unfortunately, the office closes at 6, so we don't have enough thing to ship the load. But you can see the NPCs try to ship the load at least like 4 to 6 p.m. In the morning time or earlier time. So we actually had a little savings, and yeah, that's summer test. And the bottom figure is also peak reduction, like it's the time of use. It has a more potential in this case, because we have some of the coincidence, the peak operation during the daytime, during the cooling operation, and we can reduce the MPC can reduce that operation, and then this so far it's a very huge saving, but it's more like stochastic operation. So with more data, maybe it can reduce, but so far we had a great result. Can you go next slide? So we have one more site. Actually, we're gonna have some more hopefully next year, but it's currently going on. This is a library space, and it's located in LA, and they have like high mass, but only 2 RTUs are operating very big area. And we are actually, since there are two heat pumps, so instead of having the peak demand reduction, we are trying to focusing on the dynamic pricing, low shifting. And library is in operation until 10 p.m., so we have more potential, but you can see their cooling load is very high. They're like until 8 to 10, they have the full heat pumps is fully operation. So although the heat pump is trying to pre-cool very early morning, but the shifted load is keep decreasing, and it ended up with a very small in the peak time from 3 to 10. But it's already 11% though. But thinking that they're very conservative the condition, like they only allow us to change the thermostat temperature between 70 to 72, which is we have only 2-degree freedom. And also the load characteristics we have still it is working. So I'm very glad that we have some results for this site. Okay, can you go next slide? Yeah, I think this is the final slide. So I have a lot of things to talk about, but we are trying to design the MPCs more accessible or scalable. Maybe I'm used to the technology too much, but for now it doesn't require any hardware retrofit. Like we don't need to put some power meter or airflow meter. We just need a smart thermostat. And also, as you can see, people just talking about advanced control can save energy, 20%, 30%, but you can see it depends on the load characteristics and the price signal, etc. So MPC is fortunately have a flexible structure to can accommodate price signals. So we can deal with the future changes in the utility price signal, but that very decide how the MPC is performing, is really working or not. So we need to develop how we can make that more like as a screening tool or decision tool. And we are trying to the deployment process very automated, but still it's very sometimes the thermostat is not working correctly, or like the communication is a little bit limited, etc. So we are trying to increase our portfolio more. And finally, stakeholder communication is always important. So sometimes they even didn't notice whether MPC is going on or not, although there are a lot of weird operation. But sometimes they are too oversensitive, and we don't have to let them know. But once we let them know, okay, today the controller is a little bit malfunctioning, then they just annoyed too much and then try to blame us easily. So making good relationship and trust is very important. Okay, that's it. Thank you.
Thank you, Sangwoo. This is the naked truth. We're researchers. We don't sell a product. So when it works, it works. When it doesn't work, it doesn't work. I love the idea of a tool to screen buildings that may have more potential. All right. So Ettore is going to present our work on large commercial buildings. We have John Elliott here, who has been working with us on the project. This is a building in our campus. And take it away.
Thank you, Marco, for the kind introduction. Hello, everyone. I'm Ettore Zanetti, and I'm a postdoc here at the lab. And if you can go to the next slide, I'm going to show you the building Marco was talking about. It's a large commercial building, and it's building 59 here on campus. If you want to see, you can just go down while exiting the lab on the left. You'll see it there. And in particular, we control the office space of the building, which is 2 floors. At the bottom floor, there is the computing center, which we do not have access to. And the peculiarity of this building with respect to, for example, what who was showing, apart from the fact that it's a larger building with a built-up HVAC system, is that it's served by an underfloor and distribution system, and we will see why that is important later. And to give an idea of how that works, you can take a look at the figure there on the left, where we have 4 rooftop units that basically supply air to the concrete base of the floor, and then the air seeps through the building, and then it goes back into the rooftop units. And the rooftop units provide ventilation and cooling for the building, and the MPC can control the supply fan speed of each of the rooftop units and the supply air temperature set point. And then for heating instead, in the perimeter zones of the building, there are fan coils that are served by a heat pump. And there the MPC can change the set point in each of the zones to trigger a heating request so that the heat pump will turn on and the room will be warmed up. And so the MPC integrates with the existing control logic much more deeply than it would do in smaller commercial building, and that requires a more custom interface. And this MPC can optimize for cost, energy, and CO2 emissions, but for the results I'm going to show you now, they will be on cost using the dynamic prices that we have been hearing about so far. So if you can go to the next slide. In terms of communication architecture, the core is a server in building 90, which is where my office is. And the server collects the price data from project partners and the weather forecast from NOAA, and then also all the data, monitoring data from the building automation system through a SkySpark instance from the lab, and also some additional temperature sensors that were positioned around the building. Then it runs all the calculations and the optimizations that it should, stores all the data and the results into a separate LBL server, and then the set points are sent via SOAP interface to the building automation system. And in terms of results, if you can go to the next slide. So we conducted a total of 4 2-week studies, and 1 for each season. The idea here was to try to understand what are the potential savings for this building for the whole year. And so we wanted to test the MPC in different conditions in terms of both dynamic pricings, but also in terms of weather and climate and use of the building. And in particular, in these plots, you see the blue lines are the prices, so summer, fall, winter, spring, which can be quite different. In the summer, we have a big single peak at night. In the spring, we have 2 peaks, one in the morning and one in the evening. And then also the demand of the building is different. And in general, the MPC did a pretty good job at shifting the load. And when we were talking about choosing the right building, because this building is served by underfloor air distribution system, it's able to use a lot of the thermal mass to shift the load. And so, for example, if we look at the summer, without increasing the overall consumption, actually on average decreasing it, we were able to shift a significant portion of the load away in the night doing free cooling or in the morning. And something similar happened in winter where we did preheating, and in spring where we focus more on the central hours of the day. And if you can go to the next slide, I'm going to show you an example of a typical day of operation for summer. The chart at the top is the electricity price, and then on the x-axis you have the hours of the day from midnight to midnight. And the second chart instead is the temperature for the average temperature in the whole building, and in gray are the, let's say, areas that are considered uncomfortable. Those are the temperature set points. In black is the baseline controller, and in green is the MPC. And you can see that the MPC starting pretty early in the morning or even at night will start to do free cooling and pre-cooling, slowly dropping the temperature in the building. And in fact, you can see it also from the first chart where the consumption increases. And then during, let's say, after 2 p.m., the MPC, starts to slow down the fans, slow down the cooling coils, so that the consumption will reduce. Of course, the temperature will increase, but because of the forecasting capability of the MPC, doesn't go outside the comfortable boundary. And the final result is that we can, by shifting all this load, we can save a lot of money. In fact, if we look at the last chart, which is the multiplication between the hourly price and the hourly consumption, we see that more or less when the price is very low, such as in this case, increasing consumption causes a slight increase in price, but then when the price is very important, the MPC can save even more than 50%. And in fact, if you go to the next slide, on average for the whole testing period, we were able to save around 50% in running costs. And you can see that in the scatter plot on the left, where on the x-axis you have the mean temperature. Of course, Berkeley is a mild climate, so cold days and warm days kind of blend in. But still, the building had different behaviors in terms of cooling and heating. And then the dots instead that you see are the daily cost of running the HVAC for that specific day. The MPC days were in pink, and in orange instead are the baseline controller days. And looking at the trend lines, clearly the MPC is able to save costs more or less throughout the whole year. And then those regression lines could actually be used to estimate the yearly target costs for savings. That's what we did in a publication that's soon to come in a journal paper. And of course, all of this should not come at the cost of comfort. You saw it anecdotally in the day that I showed you before, where the MPC increased the temperature but did not reach the boundary. And this is also reflected in the chart on the right, where the x-axis is the same, and each dot instead represents basically for how many hours and by how much was the temperature in the building outside the comfort boundaries. And the MPC in green, while the baseline is still in orange, there wasn't much difference. There was only in some summer days were particularly hot, especially last year, like one day where the MPC struggled a bit, but that's also true for the baseline control, and that's a problem of the building itself. So if you go to the next slide, to summarize, we were able to show that the MPC can shift the load in many different conditions in terms of pricing and boundaries, and all of this is done without changing the code. So I think that's the real benefit of MPC, as also Senhus was highlighting. MPC structure is flexible and can adapt to all of these different conditions. However, because MPC requires real-time data as a feedback when we control, every data loss, every communication loss actually becomes critical. And how do we handle these communication losses, especially the more complex the system we control becomes, and the more data streams we are controlling, the more this is important. And then to elaborate a bit more, for example, last year when there were wildfires, in the summer tests, the facility managers closed the outsider dampers, and because they didn't want smoke to enter the building. And while I was looking at the results the morning after, I was seeing that the consumption of the MPC suddenly went like tripled with respect to what I was expecting, because the MPC was still thinking that it could do pre-cooling for free, just running the fans and opening the dampers. But that did not happen. Instead, it was recirculating the air, running the cooling coil at full power. And so in the end, we implemented a slight change to the MPC, which was actually pretty easy to implement, where we told the MPC, don't use, like, you cannot use outside air anymore. You have to recirculate the air. And it definitely adjusted the targets, and it was still able to save with respect to the baseline. But having a solid communication with the facility managers, or like checking the alarms of the buildings and being integrated with the overall communication infrastructure of the building, it's pretty important to have a robust implementation of MPC. So yeah, that's my take.
Thank you, Ettore. So we saw, small buildings, more generalizable, but limited things you can control. And we're going to large buildings that are more customizable, needs more customization, but you can change more things and control more things. And now we're getting to full campuses with Donghong. Go ahead.
Hello, everyone. My name is Donghong Kim. I'm a research scientist working on a model predictive control for about 15 years or something. I have worked on small commercial building, medium, large, but one of the most attractive project would be this project handling the campus-wide systems. I will talk about like what type of system I'm handling. Next slide, please. So in this presentation, we are presenting two results. One is collaborating with the UC Merced, and the system that we are handling is the large chiller plant that actually serves all the entire campus of the UC Merced. This figure shows the 2 million gallons of water tank, and it's like a 30 feet diameter, 30 feet height. It's a huge tank, and it has around 5,000 refrigeration ton chillers, and also 9 cooling towers. And in addition to that, we have around 5 megawatt solar farm is also providing renewable energies to the campus. And there, our problem is by getting the dynamic price signal from the grid, how can we coordinate those different distributed energy resources in order to maximize the benefit into the campus, basically reducing the utility cost while maximizing the load shifting capabilities so that grid can benefit. Another side is collaborating with the UC San Diego. We have around 1.5 megawatt scale battery energy storage system. That's around the 2 megawatt hour, that is able to shift around the 2 megawatt hour, and also around 30 EV charging stations. That's also other distributed energy resources. Especially with the EV charging stations, we are not just handling the one EV charging. We are handling multiple here in this demonstration case. 30 EV charging stations. And you can imagine that different car owners around a different time, and they left, in a different time. So the kind of departure time, arrival time for each EV charging station is different. So so you can imagine that how it would be difficult to coordinate all the different stochastic the EV charging station problems. Next slide, please. This slide shows the communication architecture. I think it's pretty similar to what previous speakers are mentioning. We have for all different distributed energy resources, we have an MPC server that's communicated to the different type of management system that is connected to all the sensors and controllability to the different DERs. And the MPC server is receiving the CalFlexHub signals and also communicating with the different management system in order to find out what's the best optimal solutions in response to the dynamic price signal. Next slide, please. This is a little bit more detail of the UC Merced campus cases. One thing that I'd like to emphasize is a little bit more detail about the model predictive control flow. We are receiving the weather forecast and also the solar, because we have a 5 megawatt renewable solar farm. We are getting PV forecast and the grid signals, and MPC server based on the updated measurement of EMS that includes what is the state of charge in the chilled water tank, and what's the current PV generation, what's the current building load, and that kind of stuff. And based on the updated measurement with the model, built-in model, it is able to forecast what's gonna be the load profile looks like, and basically trying this approach and that approach. Since we have a model, we is able to predict what's gonna be the cost, what's gonna be the load at different time. And this model predictive control is basically trying and errors and find out what's the best optimal decisions for the future. Next slide, please. This is the field test result for a cooling plant. The first figure shows the chiller plant power. That includes only the 5 chillers and also the cooling tower pumps. And this is state of charge, basically representing what is the height of the chilled water stored in the tank. And the last figure shows the campus net power, including the chiller power plant. That includes all the power consumption in the buildings and the others. One thing that I wanted to emphasize is that this is the period when the price rate is high. Since we are utilizing dynamic price signals, it's not really deterministic. It has some like a different decision for different days. By the way, we have implemented this for several continuous week, and this is why we have this box plot rather than just a point. But inconsistently, when the price is high during a summer, so we try to not to utilize the chiller power. Instead, we wanted to utilize the energy stored in the chilled water tank so that we can reduce the load. Instead, we have to charge the energy in advance so that during the daytime, especially in this case, leveraging the on-site renewables. Leveraging the on-site renewable, we are running the chiller a bit more higher than the other time period, which is completely opposite than other kind of conventional summer energy ice storage strategies, which like charge during a nighttime and leverage utilize the stored energy during when the price is during the afternoon period. So the megawatt hour scale is that and 2.5 megawatt load reductions. That make me very exciting and interesting because we only deployed a single controller, and that resulted in a megawatt scale, a reduction, or the load shifting. In order to make this kind of if same effect, maybe using the different device level, we may have to deploy like thousands of control infrastructures and controller communication, but this one is able to show us only one single deployment and very effective. Next slide, please. This is the test result of a better energy storage system. Quick summary. This is the test result with the two peak price signal and one peak. The blue one or the red one is actually what MPC is doing. When the price is low, it try to charge. When the price is high, it try to discharge so that we can reduce the load. You can check the charging and discharge by looking at the state of charge of the battery in here. One of the key emphasis is around $1,000 revenue for each day because of the size of the battery energy storage system. Next slide, please. And this is the result of field test result of EV charging stations. We compare the different baseline strategies. One is just the existing baseline, that's actually the measurement. And the other one is whenever whoever just arrived, just provide constant power until the car is departing. So that's the constant P strategies. And VOG is when just EV car is plugged to the EV charging station, just provide the maximum power at the EV charging stations to meet the fully until it's fully charged. We compare these three different baseline strategies, and this is the savings result compared to the baseline and others. Like this gray area is actually the cost summary over the multiple day test, and it achieved like a 50% reduction in the cost compared to the baseline, and even compared to other like a POG that sounds like the most intelligent control strategies, we achieve a very significant savings and also the load shifting result. And the last slide. So the key message is simple. So using this large scale system, we can very effectively shift the load and also create the benefit. Like for the EV charging station, no, the battery energy station, $1,000 per day, but the UC Merced case or other cases, it could be up to $10,000 per month savings. So I think it's a really great distributed energy resources to make a decarbonization in the grid. So since it's such a kind of infrastructure, especially the chilled water tank, that there are many campuses and district energy systems that already have. Why not maximize the utilization of such an existing infrastructure for the load shifting? And one of the ideas is collect such large number of distributed energy systems, including UC Merced and other colleges and the UC San Diego. We try to achieve and demonstrate these technologies for the grid decarbonization and the virtual power plant. I think this is it. The only things that I'd like to add is for this proposal is not determined yet, but U.S. Department of the Energy is co-sharing these ideas. So we would like to get some finger crossing for this proposal. Thanks so much.
Thanks, Ngong Kung, and I want to acknowledge Jan Flesl.
Jan
Last
Clausen,
name is
yep.
challenging. The PI from San Diego who run the experiments over there. So it's later than I thought. So I have my own questions, but I would like to hear the audience first, and then if there's no more questions, I can ask a few.
Thank you very much. Impressive presentations. My name is Joram from Nostromo, thermal energy storage for HVAC, for air conditioning. Also specifically for chiller or chill water cooled systems. And my question about the district project, you have a very significant storage capacity there, both the batteries and the cooling and the water tank. So I guess two questions. One is the savings, what component of that was driven by dynamic prices versus rates or whatever your costs are? And number two, did you look at ROI because you got some pretty significant infrastructure there? So
Yeah, that's a good question. It's a little bit like for this project, it's a little bit difficult to calculate return of investment because chiller semi-energy storage is already there. The only investment is our control upgrade and resulting, and also all the sensors and BMS system is already built in the majority of district energy systems. So return of investment is like payback period is just extremely short, like I don't know, a month, 2 months, maybe. But it really depends on what's the available infrastructure. But the using Mercedes case, I guess like 1 or 2 months. Majority of actually saving is coming from the demand reduction rather than a load shifting, because UC campuses, I'm not sure it's a generalizable, but some of UC campuses has a special kind of direct purchase agreement of the electricity, so their price is pretty flat, but the demand charge is huge. Yes.
I just want to add the question of should we have a tank like this in every campus is a good one, and I think we should study that because it could be beneficial to the whole state.
Hi, Tristan DeFrandeville with Skycentrics. So on your winter test results graph, our first speaker, you basically had a blue peak that was super high. And then on the same graph, you have a green peak that is 42% lower. You say peak reduction 42%. So number one, what is that green peak? I mean, it is interesting. My prediction of what it is that it is, hey, we lowered the blue peak by a lot. And to be able to do that, we had to get a little peak, and the little peak was 42% lower. And then interestingly enough, right, I'm also part of the CalFlexHub, and I've been told that when we do commercial building stuff, we're not supposed to run any peak demand charge mitigation at all. We're just supposed to run the prices. So you're bragging about, in your case, the peak demand charge reduction. And you just talked about how high the peak demand charges are. So I guess that's my theme of the day. What are these peak demand charges all about? And did you truly reduce them? And was that, as you say, 30% cost savings? So that's what you bragged about. And I do understand that the Midas real-time pricing isn't here yet, but I'm just curious if you could speak to that green and the peak demand charge. Thanks.
Oh yeah, thank you for the question. And yeah, I had no time to share every details. So first of all, we tested two price signals. The first one is the dynamic price signal. So there's no demand charge. So we can only have a saving from the dynamic pricing. So that's the top figure. The bottom figure is typical time of use rate. So the utility charge their peak demand charge based on their monthly peak demand. So we try to test our technology, either dynamic pricing or just typical regular time of use, so that any like small, medium commercial buildings can use our technology. And yeah, that's the rationale of why I try to measure the two experiments. And the second, about the first question about the green peak. Yeah, there's a like interesting story, because MPC is a supervisory control. So we are trying to control the thermostat, but the user also can control the thermostat as well. So even though we let them know we are doing MPC, but in a practice we don't want to interrupt their comfort and their sense of mind of the controllability. So we allow them to override thermostat. So when they override thermostat, we stop our MPC for 3 or 4 hours. That's like based on our discussion before the experiment, and then MPC stopped the controlling that part. So because of that override action, so sometimes the users suddenly coincidentally they just override several devices at the same time. Sometimes they can be cooling or heating, whatever, although it's a heating season or cooling season. So by doing that, they make some like uncontrollable peak demand. That's why we have the green peak. That's not our desired output, but yeah, because that reason we need more data. But yeah, essentially, but still, by using that, but MPC still can detect how many thermostats are overridden. So based on that constraint, we try to minimize the other units on like unnecessary operation. So still, we can get some demand savings. Yeah.
And Kirsten, just to provide a little bit of clarity, this project is co-funded by CalFlexHub, and so the prices you see or dynamic prices are the results of CalFlexHub, but the other things you showed are part of a different project. They are just for comparison, for like, you know, reality check with what people pay right now. So you're right. We're not supposed to do that, but still people pay those things and those prices right now, and so that's the context, just to.
I guess this is a question for any of the three speakers. My experience has been that anytime you do some sort of load shifting, in most cases, there's an actual energy penalty compared to just optimizing on energy. There's a few rare exceptions to that, but if it's batteries, you generally have some round trip efficiency losses. It's the same in thermal storage systems. In any of your three studies, did you look at the difference between optimizing for energy, total energy consumption in the absence of the price signal versus the price signal, and how much of a difference was there? Did you consider that kind of energy penalty overall in the studies? Thank you.
I can try to reply. We definitely considered it, and you're right. Unfortunately, we did not run a specific study on that. But in a previous study, someone did test MPC using energy, running it with an energy minimization objective, and the results are pretty similar. And one of the reasons I mentioned at the beginning is that it really depends on the round trip efficiency that you have on your flexibility. In our case, because the building is pretty new, it's fairly well insulated, and we were actually activating the thermal core, like the concrete core of the building, that thermal shift did not affect much the energy consumption. And actually, I didn't show it in the slides, but these MPC still uses less energy, especially in winter and fall, than the baseline. So I'll say, in general, usually you start from a baseline controller and not necessarily an MPC optimizing. So sure, there is a bit of a trade-off, but given where we start from, which is the baseline controller, on average, the MPC will still do a better job, even with a different objective.
And Ettore, I think you mentioned reheat, right? So you're like, because it's heating and cooling.
Yeah, both in heating and cooling.
That's
yeah.
a source of efficiency that
Yeah.
beyond it.
I'd like to add two interesting story. One is using a small Ettore just mentioned new building, but I have been working with some like the old building built in like 100 years ago when I worked at Purdue, and energy penalty was huge, like 60% consuming more energies. But that's because the objective function of the MPC is to minimize the utility bill rather than the energy cost. So energy dollar, the kilowatt hour. So that's really depending on what the objective function is. And the second story regarding this chiller plant, when we operate the chillers during the hot days, right? There's a penalty of the chillers because of the increasing condensing pressures. But it's getting complicated because we have on-site renewable over there. Is there really like, the inefficient, if we consider the on-site free, renewable energy generation, equipment itself, maybe it should be inefficient because we are running very high condensing temperature. But in a system wise, I guess it's getting complex. Yeah.
Last lingering question? Any last question? All right. Well, come back next year. You'll hear about the other 15 sites that Sangwoo is working on. There are other 4 sites, and well, maybe I'll get a chance of asking my questions about the business model and the level of R&D necessary to bring this to market. Thank you, everybody.